What if I told you your browser has been able to run C++ at near-native speed for years, and most developers have no idea? Not a JavaScript framework, not a transpiler, not a polyfill. Actual compiled binary code running inside your browser tab at speeds close to what you'd get from a native desktop application. That's WebAssembly. And it has been hiding in plain sight since 2017. I'm Alex, and this is Bot Thoughts by AmtocSoft. Today we're diving into WebAssembly, what it actually is, why it matters, who's already using it in production, and where this whole thing is heading. Because I think WASM is one of those technologies that most web developers underestimate until suddenly they can't ignore it anymore. Let's get into it. Okay, so what actually is WebAssembly? At the most basic level, WebAssembly, or WASM, is a binary instruction format for a stack-based virtual machine. I know that's a mouthful. Let me translate it. Think of WebAssembly as a kind of universal bytecode. You write code in C, C++, Rust, Go, or a handful of other languages. You compile it to WASM instead of compiling it to native machine code for your CPU. That WASM binary gets shipped to the browser. The browser's WASM runtime executes it. The key insight is this: that execution happens inside a sandboxed environment at performance levels much closer to native code than JavaScript can achieve. We're talking about 1.5x to 2x slower than native in typical benchmarks, which sounds bad until you realize JavaScript is often 10x to 50x slower than native for computationally heavy tasks. WebAssembly was designed from day one to complement JavaScript, not replace it. It's not trying to take over your entire web app. It's trying to give you a high-performance escape hatch for the parts of your code that are genuinely compute-heavy, and it was designed with security in mind. WASM runs in the same sandboxed environment as JavaScript. It can't access your file system, it can't make network calls, it can't do anything that the browser hasn't explicitly permitted. That sandbox is a feature, not a limitation. It's what makes it safe to run compiled code from an arbitrary website. Here's where it gets interesting. JavaScript has come a long way. V8 and SpiderMonkey are engineering marvels. JIT compilation, hidden classes, inline caching, modern JS engines are incredibly fast, but there's a ceiling. JavaScript is a dynamically typed language. The engine has to figure out types at runtime. It has to handle garbage collection. It has to deal with the fact that any variable could be any type at any time. All of that creates overhead that you fundamentally cannot engineer away, no matter how smart your JIT compiler is. WASM doesn't have those problems. The types are baked in at compile time. There's no garbage collector unless you bring one with you. The binary format is compact and fast to parse. The engine knows exactly what it's going to execute before it starts. For certain workloads, this is a night-and-day difference. Image processing, video encoding and decoding, audio processing, game physics, cryptography, machine learning inference, scientific computing, PDF rendering. These are all tasks where JavaScript hits its ceiling and WASM accelerates past it. And here's the part that most web developers miss: you don't have to write WASM by hand. Nobody writes raw WebAssembly the way you might write raw assembly. You write in Rust or C++ or even Python in some cases, and the compiler does the heavy lifting. Let me give you some production examples because this isn't academic. Figma, you know Figma, the design tool that basically ate Adobe's lunch. Figma runs their core rendering engine in WebAssembly. Their canvas is a C++ rendering engine compiled to WASM. That's how they get desktop-class graphics performance inside a browser tab. They've written about this publicly. Without WASM, the Figma experience as we know it wouldn't be possible in a browser. Adobe. Photoshop on the web. This is a big deal. Adobe spent decades building Photoshop in C++. Rather than rewrite everything in JavaScript, they compiled their existing codebase to WebAssembly. The core image manipulation engine, that's C++ running as WASM in your browser. Layer blending, filters, masking, all of it. Google Earth. Billions of 3D tiles, real-time rendering, coordinate transformations. Google Earth on the web uses WebAssembly extensively for its geospatial computation. It's what lets you fly around the globe in a browser tab without a native app. Autodesk. AutoCAD running in the browser. Again, a massive C++ codebase compiled to WASM. What would have been completely impossible with JavaScript is suddenly practical, and it's not just design tools. Cloudflare Workers supports WASM. Fastly's compute platform runs WASM at the edge. In gaming, Unity and Unreal Engine both have WebAssembly export targets. FFmpeg, the ubiquitous video processing library, has a WASM build. There are entire SQLite databases running in the browser via WASM. This technology is in active production at some of the most sophisticated software companies in the world. I want to be careful here because this is where the hype can get ahead of reality. WebAssembly is not JavaScript's replacement. This is important. If you have a typical CRUD web app, a dashboard, an e-commerce site, a content platform, rewriting your JavaScript in Rust and compiling to WASM is not going to help you. Your bottleneck is database queries and network latency, not CPU cycles. WASM would add complexity with essentially no benefit. WASM wins when your workload is genuinely compute-bound. The heuristic I use, if you'd normally reach for a native binary or a background worker for this task, that's a candidate for WASM. There are also some real friction points with WASM that you should know about. First, startup time. WASM modules need to be compiled and instantiated. For large modules, this can take hundreds of milliseconds. There are streaming compilation APIs that help, but it's still a consideration. Second, DOM access is indirect. WASM can't directly touch the DOM. It has to call through JavaScript to manipulate HTML elements. There are proposals to improve this, but today it's a genuine limitation that means most WASM-heavy apps use JavaScript as the glue layer for UI concerns. Third, debugging. The developer tooling has improved dramatically, but debugging WASM in dev tools is still not as smooth as debugging JavaScript. Source maps help. The situation is getting better, but it's not effortless. Fourth, binary size. WASM binaries can be large, especially if you're including runtime overhead from things like garbage collectors. Rust tends to produce lean WASM binaries. Go's binaries are much larger because the runtime is included. This matters for load time. So the decision matrix looks like this: JavaScript for UI logic, event handling, API calls, and anything that touches the DOM. WebAssembly for compute-heavy algorithms, cryptography, image or video processing, physics simulations, and anything where performance is genuinely critical. Here's where this gets really interesting for 2026 and beyond. WebAssembly was originally designed for the browser, but the people building it quickly realized something. The sandbox model that makes WASM safe in browsers also makes it incredibly useful outside of browsers. Enter WASI, the WebAssembly System Interface. WASI is a standardized API that lets WASM modules interact with the operating system. File system access. Networking, clocks, random number generation. Standard in and out, all through a capability-based permission model where the host controls exactly what the WASM module can access. What does this enable? It enables a universal binary format for server-side code. Imagine writing a piece of code once in Rust or C++ or any WASM targeting language and running it anywhere, on the server, in the browser, at the edge, on a Raspberry Pi, in a container. Without recompiling, without porting, without a platform-specific runtime. This is not science fiction. Docker's creator Solomon Hykes said, and I'm paraphrasing here, that if WASM and WASI had existed in 2008, Docker would never have needed to be invented. Cloudflare Workers is already built on this model, so is Fastly Compute. The concept of running WASM at the network edge, code executing close to users, in isolated sandboxes, with startup times measured in microseconds, is a real production architecture in 2026. The component model is the next evolution here. The idea is that you can compose WASM modules together, regardless of what language they were written in. A Rust module and a Python module and a Go module can be linked together into a single WASM component. That's a genuinely new model for building polyglot systems. WASI 0.2 landed as a stable release, and the ecosystem is building around it quickly. If you're following server-side JavaScript or edge computing trends, You're going to hear a lot more about WASI in the next 12 months. So if you want to actually get your hands on this, where do you start? My recommendation: start with Rust and WasmPack. Rust has the best WASM toolchain in the ecosystem. WasmPack handles the compile step, generates JavaScript bindings, and produces an NPM-compatible package you can import in any web project. You write a Rust function, you annotate it with a macro, you run WasmPack build, and you have a WASM module you can call from JavaScript in minutes. If you're a C++ developer, Emscripten is the established path. It's how Figma and Adobe compiled their existing code bases to WASM. It's mature, well-documented, and handles a lot of complexity for you. If you'd rather stay in JavaScript land and just consume WASM rather than write it, that's totally valid too. There are WASM builds of popular libraries: SQLite, TensorFlow, FFmpeg, OpenCV, that you can drop into your project and call from regular JavaScript without touching a system's language. The lowest friction starting point. Grab a computationally heavy algorithm you already have, something that crunches numbers or processes data, and try porting it to Rust plus WASM. Measure the before and after. The performance difference for the right workload is one of those things that makes you stop and reevaluate what's possible in a browser. WebAssembly has been in your browser for years. Figma, Photoshop, Google Earth, some of the most ambitious software ever shipped to the web runs on it. And with WASI, it's expanding beyond the browser into servers, edge networks, and embedded systems. The web platform is a lot more powerful than most developers give it credit for. WASM is a big part of why. That's it for this episode of Bot Thoughts. If this was useful, hit follow or subscribe wherever you're listening: Spotify, Apple Podcasts, YouTube. We publish new episodes every week on AI, software engineering, and the tools that are reshaping how we build. The link to the full blog post on WebAssembly, with code examples, benchmarks, and the WASI explainer, is in the show notes. I'm Alex. Thanks for listening. See you in the next one.